Hi friends, today I am giving a lecture on P problems, NP class problems and NP hard problems. So suppose we can take a problem, that problem may be solved in polynomial time or non-polynomial time. So problems can be classified into two groups based on that condition. Suppose if the problems are solved in polynomial time by using deterministic algorithms, so that problems are polynomial time problems. The second group consists of the problems that can be solved in non-polynomial time. So that problems are called exponential problems. So here the first group is nothing but polynomial time problems, because the problems that can be solved in polynomial time by using deterministic algorithms. Example, searching an element from the array of given n elements. So that can take, the time complexity is big O of n. Searching of an element from an array of n elements by using binary search, its time complexity is big O of log n. Suppose we have to find out the shortest distance between every pair of vertices. So then it is called as all pairs shortest path problem. It can take big O of n cube time complexity. Next, matrix addition. So its time complexity is big O of n square. Next, matrix multiplication. Its time complexity is big O of n cube. So these are called as polynomial time problems. Okay. So for these problems, we have to solve these problems within the polynomial time. So then we can say that these problems are called as polynomial time problems. Next, the second group consists of the problems that can be solved in polynomial time by using non-deterministic algorithms. So that type of problems are called as exponential time problems. Example, traveling salesperson problem. Its time complexity is big O of n square into 2 power n. Second one is nap 0 by 1 knapsack problem. Its time complexity is big O of 2 power n by 2. Third problem is graph coloring problem. Fourth problem is Hamiltonian cycle problem. So these are the problems that can be solved in exponential time by using non-deterministic algorithms. So these problems comes under exponential problems. So these are the two groups the problems can be classified. First one is polynomial time problems. Second one is exponential time problems. The problems that can be solved in polynomial time by using deterministic algorithms. So these are comes under the first group. The problems that can be solved in polynomial time by using non-deterministic algorithms, so that problems comes under second group. Okay, next, what is deterministic algorithm? Okay, suppose we can take an algorithm in which every operation is uniquely defined. So then that type of algorithm is called as deterministic algorithm. For example, suppose we are at Q naught state. So Q naught state with the input A, it can goes to only Q1 state. Okay, here we are at state Q naught. Q naught state with the input A, it can goes to compulsory Q1 state. There is no alternative is there. Okay, so that type of algorithm is called as deterministic algorithms. So polynomial time problems can be solved by using deterministic algorithm in which every operation is unique. Okay, every operation is uniquely defined. So that type of algorithm is called as deterministic algorithms. Second one is non-deterministic algorithms. So the algorithm in which every operation may not unique. Okay, instead there is a set of possibilities are there. Set of possibilities are there. So that type of algorithm is called as non-deterministic algorithms. So for example, so Q naught state with the input A, it can goes to Q1 state, or it goes to Q2 state, or it goes to Q3 state. Okay, now we are presently at Q naught state. With the Q naught state, with the input A, it can goes to Q1 state. With the input A, same input, it can goes to Q2 state. With the same input, it can goes to Q3 state. Okay, so there is a set of possibilities for every operation in non-deterministic algorithms. Okay, that means with the same input, maybe it goes to Q1 state, maybe it goes to Q2 state, maybe it goes to Q3 state. But here for every operation there is a every operation it is uniquely defined, but here it is not uniquely defined. It can goes to either Q1 state, it goes to either Q2 state, it goes to either Q3 state. So this type of algorithm is called as non-deterministic algorithm. Non-deterministic algorithm. So exponential problems are comes under non-deterministic algorithms. Polynomial time problems comes under deterministic problems. Okay. So that is the main difference between deterministic algorithms and non-deterministic algorithms. So we have already know the difference between DFA and NFA. Deterministic finite automata, non-deterministic finite automata. Same deterministic algorithm, the same difference can be applied to deterministic algorithms and non-deterministic algorithms. Okay. Next, the problems computationally solvable are divided into three classes. First class is polynomial class problems. Second one is exponential time problems. Third one is intractable problems. P class problems. The problems that can be solved in polynomial time by using deterministic algorithms is called as P class problems. So here P stands for polynomial time. So examples for P class problems are searching a given element from a array of given n elements. So it can take time complexity big O of n. Second one is sorting of given n elements. So its a time complexity is sometimes big O of n square and sometimes big O of n log n. Third one is matrix addition. So addition of two matrices. So its a time complexity is big O of n square. Next one is matrix multiplication. So big O of n cube. All pairs shortest path problem, big O of n cube. So these are the problems. So these problems can be solved in polynomial time by using deterministic algorithm. Okay. Second one is NP class problems. The problems that can be solved in polynomial time by using non-deterministic algorithms. So the same definition can be stated in some books as the problems that can be solved in non-polynomial time or that can be easily verified in polynomial time by using non-deterministic algorithms. So the examples for NP class problems are traveling salesperson problem. It can take big O of n square into 2 power n time complexity. Graph coloring problem, big O of n into m power n time complexity. Third one is Hamiltonian cycles problem. Fourth one is 0 by 1 knapsack problem. Its the time complexity is big O of 2 power n by 2. So these are the problems that are comes under NP class problems. NP stands for non-polynomial time. So the computational complexity problems are classified into two types. First one is P class problems. Second one is NP class problems. So again, NP class problems are classified into two categories. First one is NP complete problems and the second one is NP hard problems. Up to this point, we are already know that what is P class problems and what is NP class problems. So P class problems can be solved in polynomial time by using deterministic algorithms. So these are the examples for P class problems. NP class problems is nothing but problems that can be solved in non-polynomial time by using polynomial time by using non-deterministic algorithms. So these problems comes under NP class problems. These are the examples for NP class problems. Again, these NP class problems are classified into two categories. First one is NP complete problems and the second one is NP hard problems. This is the relationship between P and NP class problems. So here the relationship is every problem in P class that is also in NP class. So here we can say that P belongs to NP. Every problem which is in P class that is also in NP class. Second one, every problem in NP which is not in P class, every problem in NP class which is not in P class. So we can simply say that every problem which is P class that is also in NP class, but every problem in NP which is not a P class. So this is the relationship between P class and NP class. Next, P class problems can be solved efficiently, but NP class problems cannot be solved efficiently. Next one is NP complete problems. So we are already know that NP problems. So NP problems is nothing but the problems that can be solved in polynomial time by using non-deterministic algorithms. So that problems are called NP class problems. NP class problems again divided into two categories. First one is NP complete problems and the second one is NP hard problems. Suppose, what is NP complete problems? NP complete problem is nothing but a problem L1 is NP complete if and only if it satisfies two conditions. First condition is L1 is in NP. Compulsory L1 problem is in NP. That is nothing but L1 belongs to NP. Second condition is, suppose we can take a problem L2 in NP. So the problem L2 is polynomial time reducible to L1. Okay. So this is the definition. A problem L1 is NP complete if and only if it satisfies two conditions. L1 is in NP. That is, L1 belongs to NP. Second one is every problem L2 in NP is polynomial time reducible to L1. Okay. So how can you say that L2 polynomial reducible to L1? Okay. So now we can take a problem L2. Okay. So this problem L2 is polynomial time reducible to L1. So how can you say that there is an algorithm, that algorithm can solve that problem L2 in polynomial time. The problem L2 solved in polynomial time that can be reduced to L1. That is, L1 is also solved in polynomial time. So suppose here L1 and L2. Now we have to prove that L1 is NP complete problem. Okay. So L1 is to be NP complete problem. Compulsory the problem L1 is there in NP class. Second one is, now we have to take another problem in NP, that is L2. So there is a deterministic algorithm that can be solved in polynomial time for L2. So if L2 is solved in polynomial time, so then L2 reducible to L1 is nothing but, if L2 problem can be solved in polynomial time by using deterministic algorithm, so then L2 is reducible to L1 is nothing but, then L1 is also solved in polynomial time. So this problem is called as NP complete problem. So examples for NP complete problem is determining whether a graph has a Hamiltonian cycle. So that is, one example is Hamiltonian cycle problem. Second one is determining whether a Boolean formula is satisfiable. Second problem is satisfiability problem. Okay, the examples for NP complete problem is Hamiltonian cycle problem and satisfiability problem. So next, NP hard problems. NP hard problem is nothing but a problem L is NP hard problem if and only if satisfiability reduces to L1 is called as NP hard problems. So examples for NP hard problems are set cover problem, node cover problem, traveling salesman problem. Okay. So here a problem L is NP hard if and only if satisfiability reduces to L. That is, it can be written as satisfiability reducible to L. Okay, problems that is L1 and L2 are two problems. Now we have to write L1 reducible to L2. Okay, L1 and L2 be two problems. Problem L1 reducible to L2. It can be written as L1 directly proportional to L2. If and only if there is a way to solve L1 by a deterministic algorithm in polynomial time, then solve L2 in polynomial time. So what is the meaning of this one? So here L1 and L2 are two problems. Okay. Now we have to write it as L1 directly proportional to L2. When we have to write this one, to solve this problem L1 by a way by using deterministic algorithm. Okay, there is a way to solve L1 by a deterministic algorithm. So if the problem is solved by using deterministic algorithm in polynomial time, then we have to solve L2 also. Why? Because here L1 reducible to L2. L1 is already reducible to L2. If L1 is solved in polynomial time by using deterministic algorithm, so then L2 is also solved in polynomial time because L1 is already reduces to L2. So this is the meaning of if satisfiability problem is satisfied, so then we can say that that problem is called as NP hard problem. Okay, only if satisfiability problem reduces to L, so then that problem is called as NP hard problem. Okay, so this is L1, a problem considering this statement, a problem L1 is NP hard if and only if there is another problem L2 that can be solved in polynomial time by using deterministic algorithm. So then L2 is reducible to L1. Okay, so L2 is already there in NP, but it can be solved in polynomial time by using deterministic algorithm. Then L1 is also solved because L2 is reducible to L1. If L2 is reducible to L1, L1 is already solved in polynomial time by using deterministic algorithm. Then we have to solve L1 by using deterministic algorithm in polynomial time. So that property is called as satisfiability property. If satisfiability property is satisfied, then that problem is called as NP hard problems. Examples are for NP hard problems are set cover problem, node cover problem, traveling salesperson problem. Next, relationship between P and NP complete and NP hard problems. We have already discussed the relationship between P and NP class. Okay. So now we have to find out the relationship between P, NP class, NP complete and NP hard problems. Okay. So here this intersection part is called as NP complete problem. This second circle entire is called as NP hard problem. This first circle entire is called as NP complete NP class problem. This small circle is called as P class problem. Okay. Suppose, how can you say that the problem L is called as NP hard. Okay. How can you say that the problem L is called NP hard problem? A problem L is in NP. A problem reducible to L, if satisfies this property, then that problem is called as NP hard problem. How can you say that NP complete problem? A problem L is NP complete problem. L belongs to NP and L is also NP hard. So then that problem is called as NP complete problem. Okay. How can you say that a problem is called NP class problem? A problem is called NP class problem if it can be solved in polynomial time by using non-deterministic algorithm. Both NP complete and NP hard comes under NP class. Okay, within the circle both NP hard is there and NP complete is also there. Next, P class. P class problem can be solved in polynomial time by using deterministic algorithm. Okay, this is the relationship between P class problems, NP class problems, NP complete problems and NP hard problems. Next, what is Cook's theorem? So Cook's theorem is nothing but there is some universal problem is that P is equal to NP. Okay. So P is equal to NP is nothing but, so this P class problems are gradually increased, then it is P is equal to NP. Every problem is in P, it is also in NP. So then we can say that P is equal to NP. Cooks proved that P is equal to NP by using satisfiability theorem. If satisfiability theorem proves that P is equal to NP. So Cooks proved that by using satisfiability theorem, P is equal to NP. So this is the Cooks theorem. So thank you for watching this video. If you like this video, please subscribe my channel. So Divvela Srinivasarao. So thank you.